today we're diving into a really fascinating and pretty radical new idea that could totally reshape how we think about space, time, and gravity. It's a hypothesis that aims to finally unite the two great pillars of modern physics, the world of the very big and the world of the very small. And it all starts with a question that sounds simple, but the answer? Well, it's a real mind-bender.
So let's just jump right into it with that question. Think about a rock just sitting on the ground, not moving at all. Is it moving at the speed of light? Your first instinct is probably to say, no way, of course not, it's stationary. But if we could zoom in way, way down to the quantum level, the story changes completely.
Because according to this new hypothesis, the answer is a resounding yes. That seemingly still rock is in reality a chaotic storm of subatomic activity. Its fundamental building blocks, the quarks, the electrons, they're all in constant, frantic motion, buzzing around at velocities approaching the speed of light. It hints at this incredible trade-off in the universe. The faster an object moves through space, the slower its internal components have to move, and vice versa.
And this gets right to the heart of one of the biggest problems in physics today. On one side, you have Einstein's general relativity. It beautifully describes the large-scale universe as this smooth, continuous fabric of space-time. But on the other side, you have quantum mechanics, which tells us the subatomic world is granular, it's probabilistic, it's just messy. These two theories are both incredibly successful, but at a fundamental level, they just don't speak the same language. And that's the puzzle we're trying to solve. Now, to bridge that gap, this hypothesis suggests we have to start by rethinking something we all think we understand: gravity. You know, even Einstein himself referred to gravity as a fictional force. He didn't think it was a true force pulling on things, but instead the effect of something else far more fundamental.
So, what is that something else? Well, this hypothesis argues that it's time dilation. We're all taught to think of time dilation as a weird consequence of gravity, but this model flips that entire idea on its head. It says time dilation is the cause. It defines it as the difference in the local speed of light from one point in space to another, and it's this difference that actually creates all the effects we attribute to relativity, including what we feel is gravity.
Okay, so check out this thought experiment because it makes the point perfectly. Imagine you have 3 super precise atomic clocks. Clock number 1 is way out in deep space, far from any massive objects. It's ticking away at its fastest possible rate. Clock number 2 is on the surface of a planet. It's ticking a little bit slower and it's feeling a gravitational pull. But now, clock number 3, this is where it gets really interesting. We place it at the very core of the planet. Here, time dilation is at its absolute maximum. This clock is ticking the slowest of all 3, and yet it feels 0 net gravitational pull. So what's going on?
The key insight here is that gravity isn't caused by mass itself, or even by time dilation itself. It's caused by a gradient, a difference or a slope in the time dilation field. That clock on the surface feels a pull because time is literally flowing at a different rate above it than below it. It's this imbalance that pushes on an object's momentum. So think about it this way. We aren't being pulled down by gravity. We're being pushed down by the universe into the region where time is flowing more slowly. Okay, so if time dilation is a real physical field that can push on things, then the next logical question is, what's it made of? To make this whole idea work with quantum mechanics, it can't just be an abstract concept. It has to be carried by a particle. Let's start with a really helpful analogy. You know how a supersonic jet creates a bow wave of compressed air? It's moving so fast that the pressure waves it generates can't get out of its own way, creating a barrier, the sound barrier. Well, this hypothesis suggests that all particles do something very similar as they approach the speed of light. And this brings us to the star of the show, the proposed Celerity boson, represented by that symbol, Q. The idea is that it's a massless, force-carrying particle, a gauge boson. And here's the kicker. All matter is constantly radiating these bosons, but only in its direction of motion. So how would this work? The Celerity boson would have one, and only one, job: to act as a universal speed brake. Its wavefront impedes any particle that tries to cross it. And since every particle is constantly radiating this field ahead of itself, it's essentially creating its own bow wave that it can never outrun. This is what enforces the cosmic speed limit c. It's not some intrinsic property of matter, it's an external mechanism, a universal traffic law. Now, here is where it all starts to click together. By replacing this abstract idea of a smooth fabric of spacetime with a tangible field of particles, the model suddenly becomes naturally compatible with the quantum world. Let's just compare the two models side by side. On the left, you have traditional Minkowski spacetime. It's smooth, it's continuous,
and it has a hard, unbreakable speed limit. On the right, you have the proposed Celerity Boson field. It's granular. It's made of countless individual particles. And that one difference, that it's made of discrete bits, is what makes it fully compatible with quantum field theories and even allows for some very interesting potential exceptions to that speed limit. And this particle-based model seems to provide really elegant explanations for some of the biggest puzzles in quantum mechanics. For example, quantum foam, the theory that spacetime on the tiniest scales is a chaotic, bubbling mess. Well, in a celerity field model, that's not a weird exception. That's just an inherent property of a field made of countless interacting particles. Or what about quantum entanglement, spooky action at a distance? It could be explained by particles that, for some reason, don't interact with the celerity field, and therefore have no speed limit. Even the bizarre behavior of neutrinos might be explained if they just barely interact with this field. But here's the really crucial part. Does this mean we have to throw out a century of Einstein's relativity? Absolutely not. A field of particles radiating out from a source, like a star, will naturally become less dense the further away you get. It follows a simple inverse square law. And it just so happens that the mathematics describing this changing particle density is computationally equivalent to the mathematics describing a warped spacetime manifold. So this model doesn't change the answers that relativity gives us. It just provides a completely new and quantum-friendly physical explanation for why those answers are correct. So if this particle-based view of spacetime is right, it wouldn't just solve a few problems. It could have truly profound implications for how we understand the entire universe, from beginning to end. Let's take cosmological redshift. Right now, it's our best evidence that the universe is expanding. But this model offers a different take. In the very early universe, the background field of celerity bosons would have been pretty sparse. Why? Because the bosons from the most distant galaxies simply hadn't had billions of years to travel and reach us yet. Now let's fast forward billions of years to today. As those celerity bosons continue to arrive from ever more distant sources, the background density of this field would steadily increase everywhere. In a sense, the entire universe would become slightly more time-dilated over cosmic history. So think about what this means for a photon of light that's been traveling for billions of years. It's moving through a celerity field that is constantly, gradually getting denser. This increasing time dilation would act like a kind of temporal drag, causing the photon's wavelength to stretch out. What we observe as redshift, then, might not be the fabric of space itself expanding, but the predictable effect of this ever-accumulating background particle field. This model also offers some pretty neat solutions to other huge cosmic paradoxes. Think about black holes. How does their gravity escape if nothing can escape? Well, if celerity bosons don't interact with each other, they could just pass right through the event horizon, explaining why we still feel the black hole's gravity. Or, how about the Big Bang? The theory of inflation requires a period of faster-than-light expansion. If primordial matter hadn't learned to radiate celerity bosons yet, it would have had no speed limit, potentially explaining that incredible burst of growth. At the end of the day, this hypothesis proposes a fundamental shift in our thinking. It asks us to replace the image of a static, geometric fabric of spacetime with a dynamic, quantum-compatible field of particles. It offers a totally new lens to view everything from the apple falling from the tree to the grand evolution of the cosmos. And it leaves us with one last, really provocative thought. If our most basic picture of space has been wrong all along, what else might we be seeing incorrectly?